Hello and welcome. I wanted to start this class with just a brief review on matrices and arrays. There were some questions based on the homework that I think we still need to clarify some aspects of matrices and arrays that I think it'll be helpful going forward. Then I want to spend some time talking about some functions that are very useful, especially for us engineers. And there's many more functions that we're going to keep bringing up as we go into the course, but and especially in the MATLAB area. But for now, I just want to highlight some of these functions, and then we're going to move on to plotting and spend some time on the topic of plotting. And probably towards the end of this lecture and the next lecture, we're going to spend time talking about plotting. So let me first share my screen. Just a second. Okay, so now you're seeing my screen, and let me just continue with this. So we're going to look at some more commands, some more functions, and then we're going to start looking at plots, like I said at the beginning. So again, I want to emphasize the concept of matrix and an array and vectors, because I think there's been a bit of confusion on how we can use those three in MATLAB. Well, MATLAB has two different types of arithmetic operations. As you already know, it's got array operations and matrix operations. You can use these arithmetic operations, to do numeric computations, like adding two numbers, just raising an array to some power or multiplying matrices. And so matrix operations follow the rules of linear algebra, okay? But array operations do element by element operations, and they do support multidimensional arrays. In other words, if you remember, the way you do the dot product in matrices is different as just multiplying two matrices element by element. So in MATLAB, the period character, or the dot, distinguishes an array operation from a matrix operation. But since the matrix and array operations are the same, for addition and subtraction, we don't need that. We only really need it for multiplication, division, and power. So matrices in MATLAB, and in general, really, are two-dimensional arrays. Two-dimensional, and arrays can have any dimension or many dimensions. However, a vector is a one-dimensional array. So to reemphasize again, a matrix is a two-dimensional vector. It's got fit size, and all the cell types are the same. An array can have one or more dimensions. So an array with one dimension is the same as a vector. An array with two dimensions is the same as a matrix in general. So you can think of it as everything is an array, and then depending on the dimensions of that array, if it's got two dimensions, we call that a matrix. If it's got one dimension, we call that a vector. Okay, so array operations execute element by element. So for example, in this first example, where we're adding two vectors with the same size, then the first vector, as you can see, is 1 by 3, and the second vector is 1 by 3. So adding those two together, is really simple, right? Just A plus B. However, if we do an element-wise product of a scalar, in this case, we got a scalar here, and a matrix, we do need that period in here, okay? Because we're multiplying everything in the matrix A by the scalar 3, okay? So, like I said at the beginning, matrix operations follow the rules of linear algebra and are not compatible with multidimensional arrays. So another example here, if we do look on the left-hand side, we have two matrices, right? So this without the period will indicate the product of the two matrices, right? So we will do, the regular row by column, right? So if you do 1 times 3 and 3 times 1 gives you that 6, right? Remember, you multiply this row times this column to get that element. So this operation gives you the product of two matrices. However, if we put a dot or a period before the operation, that simply indicates an element by element product. So in that way, we'll simply be doing 1 times 3, 3 times 0, 2 times 1, 4 times 5, which gives you this expression here, right? So I think this example really clarifies the difference between the two. And I hope that helps you going forward. All right. So next thing I want to talk about is many of the functions. Some of them we have been using already, and some of them we have not used yet. But in the course of this lesson and in the next following lessons, we're going to be using a lot of these functions that are very useful in engineering, especially electrical engineering. And I have them in the slides. I have a summary of many of the functions that are very useful. So this will be for your reference. Excuse me, and what they do. So as you can see here, we have the typical square root, the nth root of a number, and so forth. The exponential, logarithm. We have the sine function. Some of these we have already defined in previous lectures. We have used already many times. But there's some other ones that we haven't really discussed or used, like the degree to radians that are used, or radian to degree. The sine d functions when very useful when x is given in degrees, right? And so this is mostly for a reference for you, and we'll be using them and applying them in several of the examples that are coming up. Also, some of the rounding functions, right? Like to round, to a certain integer, to the nearest integer, or to 0, or to, the highest number, or to the lowest number, and so forth. So more, like I said, the nth root of a number, the rem function computes the remainder. We have the factor which finds the prime factors of x, the greatest common denominator, and so forth. So keep this as a reference. We've used already the rand n to generate random numbers, right? We also have used the ABS, the angle, and the complex when we were dealing with complex numbers. And some of the things you can do, like the conjugate to get the imaginary part, the real part, so forth. So again, this is mostly for your reference, okay? So I want to now talk about a function that is very useful, or is useful to find the roots of a function. And it's called the roots function. So the roots function basically solves a polynomial of this type. And you have a variable to a certain power and associated with variables of other powers for the same variable, just a regular polynomial. So as we know, polynomial equations, and deals with the roots, by the way, deals with polynomial equations that contain a single variable which exponents are positive, non-negative exponents. So the function roots x returns the roots of the polynomial where the polynomial is represented by x as a column vector. And so the way to use it is really simple. Let's say, for example, we have this equation, 3x squared minus 2x minus 4, right? Hold on, let me just double check. Okay, yeah, so the way we're going to use this equation is we're going to call it. If you look at the second line in this statement here, roots calls the function, and the argument is a vector of that contains the coefficients of the polynomial we want to solve in an orderly fashion. So from the highest to the lowest. So in this example, you can see that 3 is the coefficient for x squared, minus 2 is the coefficient for x, and minus 4 is the coefficient for x to the 0, right? And so this, when you call roots, and in this case, you're going to put the result in this variable r. So when we call roots, we given it the coefficients of the equation we want to solve, and then calling it simply results in the roots for that equation, for that polynomial, and that's the solution for the polynomial, right? Another example. In this one, we want to solve or find the roots for the expression x to the 4th minus 1. So again, roots is the function we're going to use to find the roots. And in this case, in parentheses, we're going to include the coefficients of the polynomial we want to solve for. So in this case, as you can see, again, we're going to go from highest to lowest, right? So we start the highest, which is x to the 4th. The coefficient is 1. Now, there's no coefficients for x to the 3rd, x to the 2nd, or x to the 1. So we need to put a 0 where those coefficients go. You can't leave it just empty. You have to have a 0 because it indicates that in those positions, there's no coefficients associated with those powers of the variable. But we do have a coefficient associated with x to the 0, which is the last ones, and that one is equal to minus 1. And that's how we end up with this vector here. That includes the coefficients for the polynomial. We give that to the roots function, and then the function simply solves it. In this case, is a complex solution. Okay, so the roots function solves polynomial equations of this form, and the polynomial equation has a single variable, in this case x, and the exponents are positive. Okay. Okay, so use of the poly function is another one that we're gonna implement. Okay, and the poly function is used to get a it's like the inverse of the root function. We're gonna use the poly function to obtain a polynomial from the given roots. So in the previous case, we have an equation to find the roots. In this case, we have the roots, and we're going to find, the polynomial associated with those roots. And the format is you have the function name is called poly, P-O-L-Y, and the argument is r in this case, where r is a vector, and the function is going to return the coefficients of the polynomial whose roots are the elements of R. And if A is a matrix, then the argument is a matrix, and A is going to be an n by n matrix that returns the n plus 1 coefficients of the characteristic polynomial determined by this matrix. If you remember this from really high school, maybe linear algebra, which you don't have to know, but that's what it's solving for. Is it's solving for this determinant, right? But what we need to know is the following. Let's say we have a matrix with these values here, right? And we're going to use the poly. First, we're going to find the eigenvalues associated with this matrix, right? So we have a 3 by 3 matrix, and it's got these values here in it. And this is another function, by the way, that is used to find the eigenvalues. If you haven't seen eigenvalues, don't worry about it. It's basically the roots of that equation. And so when we call that function, right, the important thing is that it returns the complex numbers associated with those roots, right? And we call those roots the eigenvalues. Now, we haven't still used the poly function, but I just want to show you that if we have any matrix like this, we can find the eigenvalues by using this function EIG. Okay, and the idea is that since the eigenvalues in E right here are the roots of the polynomial, right? So the eigenvalues associated with this polynomial of A are given by these numbers here. So we're going to use the poly function to then find the characteristic polynomial from the values in E. Okay, so these are the roots of this matrix. So again, remember the poly function is the reverse of the root function. So if we give it the roots in this case, or which are contained in this variable E, and we call the poly function, we're going to play the result back in this variable P, and now P has the polynomial coefficients associated with the equation that generated these roots. To check, we can go back to the root equation. And remember, in the root equation, we're going to call roots, and we're going to give it the coefficients associated with the polynomial. So in this case, are the ones we got from the poly function. So if we put this in the argument, and we use roots to find the roots of this polynomial, we get this result, which is, if you look back, are the roots of the polynomial. So in the first case, we find the roots, but we know what the roots are, and find the characteristic polynomials from the poly function, okay? And then we use the characteristics of the polynomial from the roots from the roots equation to find the actual roots, okay? So again, one is you can go from roots to find the polynomial, or you can go from the polynomial to find the roots, okay? The next function I want to talk about is the f0 function. And the f0 function is used to find the roots of nonlinear equations. In fact, you can use f0 to do the job the roots does. But roots deals with linear equation, and with f0, we can deal with nonlinear equations as well. So the roots function works only with polynomials. The f0 function is more broadly applicable to other types of equations. And the format is that we call the function by the name f0, and the arguments are a function. In this call, we call fu and c, and a point that we call a0 in this example. So, and the idea that this is used to give a point of reference where the function is 0, okay? So what the f0 function is doing is trying to find out where the function crosses the 0 axis, okay? In other words, I want to know where this function here crosses the 0 axis. And the way it works is that you give it a guess. In other words, for instance, right? Think of a0 as a guess, where you think that 0 is going to be located. You don't have to know it precisely, but it gives the function a starting point, if you will, okay? Or where to go to find that 0. So the f0 command is important to understand that the f0 command doesn't really find a 0. It's going to give an approximation to the 0. It approximates the roots of the equation by finding a point where the function changes sign. So it's by the change of a sign that the function samples this f0 function samples the function you're giving it until it thinks it has found a zero in the function itself. For example, we want to find the value of the cosine function when it is 0 near to 4. Okay, so in this case, let's find a function 0 to the function x to the third minus 2x minus 5. Let's see. Oh wait, let me just do. Hold on a second. Let me just do. We'll do this in a little bit. Let me do one that'll be more obvious first, and then we'll deal with this one. So on this one, let me I think it'll make it more clear because it's more graphical. We looking at the function on the left, we're looking at the function as q. If you plot that function is from the function itself, right? We can tell that the function touches 0 at 0, right? It's easy to see. If we modify this function and we now plot x to the third plus 3, right? It moves the function up on the y-axis, right? To the towards the top of the y-axis by 3. And so here we can see, we don't know exactly where the function crosses 0, right? You can, by the arrow, you have an idea where that might be, which might be guessing, right? It could be around minus 1.5, right? That's a guess. But if you want to know exactly where that function crosses 0, then we can, make use of this f0 function. So on the first case, right, in the first case, it's obvious almost that the function is going to cross 0 at 0, right? The second case is not that obvious where exactly that point is going to be. So we're going to do a little commands to find out where those zeros are located using the f0 function. In the first case, on the left-hand side, we give it the argument, I'm sorry, we give it a function. And anytime we use the function or we define that function with using the f0 command, we're going to use the at symbol followed by the function you're trying to solve. So in this case, the variable, rather, followed by the variable you want to solve. So in this case, we have at, right? We're defining f at the variable in parentheses, and the function follows, right? So we have the function x to the third. And then when you call the f0 function, first of all, the result of calling this function in this example is going to be placed on this variable that we call 0. So we call the function f0 with the function, like we said before. Let me go back. Right, we call the function f0, we define the function, and we give it a guess, if you will, or where that 0 is located for this function. Now, when we define this function, as you saw here in the example, we use that at symbol. We'll have a little more to say about that at symbol, how it's used later. But for now, just remember that when we define the variable, we give it an at symbol of that variable. So in this case, again, if we use the f0, we have the function followed by, where we think the 0 is located, right? But we already have defined what that function is by giving it the variable and what the function actually does, right? So when we call the function, the answer is 0, as we thought it was going to be, right? There's no surprise here, but it's telling you that we were correct in that assumption. This is the second case, though, where we're not so sure where that 0, where x crosses 0 at that location. So we use the same thing, but now just to show the different function, we shifted the function up by 3, right? It's the same function, just shifted up by 3. So again, we define this function f with the variable at x, and now is defined as x to the third plus 3. And we call the function the same. As you can see, is the same call. And we give it a guess, and we say, well, let's assume that 0 is at 0. Well, no, now the function returns the actual value, where this function crosses 0, and in this case, is minus 1.4422. And you can make it more accurate if you want by defining the format to give you more decimal places. But as you can see, it's pretty close to what we thought it was going to be, but there's a difference, right? And that's what the F0 function does. So the first guess is correct. The second, the program gives you the right number. And so for this function to work, F0, the actual function you're using has to cross 0 somewhere. Okay? If the function doesn't cross 0, you're either going to get an error, or you're going to have to use some other function to find an approximation. Okay, because a function may never cross 0, right? But so F0 doesn't work for functions that do not cross over the 0 line here. Okay, but very useful for those that do. Another example, in this case, we plotted this sine wave, right? And at this point, we don't know, and I use the plot to tell me where the function crosses 0, right? So in this case, using the plot itself, I found out where the sine function here crosses the 0 axis. And it's giving me that expression right here. Now, if I use the F0 function, then I can see that this result is very accurate. And again, I want to point out first how the function is called, right? I'm going to call the F0 function. I'm giving the function I'm studying, if you will, and I give it in a guess, if you will, right? And I'm going to put the result back in a variable called value. All right. To use it, however, I'm going to have to define what f is and what x0 is. So f is defined as the sine function. And in this case, again, I'm using that at sign here to reference that function here. This is sometimes called a handle or like a nickname for the function, if you will. So, and that's the way the F0 function works. You give it that nickname or that handle. So in this case, f is the at sign function, okay? And the guess that I'm given is 3. I run it, and it gives me the actual value of 3.1416, which is, sort of what we knew already from the plot itself, okay? Now, the F0 function, like I said at the beginning, can also be used to find the roots of polynomials, and we'll see how more of that when we study how to write functions later, okay? Another function that is very useful is the polyval function. And the polyval function is used for evaluating a polynomial at specific values. And it's very clear, right? And this is the nice thing about MATLAB. You can find a function just for about anything you want. You don't have to write code because there's a function for just about anything and everything that you need. The value of MATLAB comes into how you use those functions and how do you manipulate the numbers like matrices or arrays to find what you're looking for. So you don't really spend a lot of time running functions like in the old days, programming when you have to write a function just for about everything. There wasn't a function for things that were sort of normal. MATLAB is different because, like I said, it's got a function for just about anything that you need. It's rare that you're gonna have to write a function from scratch. You're always gonna have some kind of help. So that's the usefulness of MATLAB. Okay. So again, going back to the polyval function is used to evaluate a polynomial given a value. So in the first example, we have this polynomial here, and we want to evaluate, or we want to know the value of that polynomial when x is equals 4. So the way you use the polyval function is very similar to the poly function in the way that you give it as an argument. Of course, you're going to give it the vector, and that vector includes the coefficients associated with the polynomial, which in this case, again, is going to be 1, 7, 0, because there's no x to the second, minus 5 and 9. So those are the coefficients you simply call polyval with the name of the vector that contains the coefficients and the value that you want to evaluate, right? So the second part of the argument is the value you want to evaluate this at. And that's it. Once you submit this, you get the answer. So this is the value of this function evaluated at x equals 4. Another example, we have this function here, 3x squared plus 2x plus 1. And now we want to evaluate at a different point. So we want to evaluate the function when x equals 5, 7, and 9. So again, the format of the arguments is the same. If you look at we're going to call the polyval function with the vector that includes the exponents, not the exponents, sorry, the coefficients associated with the polynomial, right? So P here in this example includes the coefficients 3, 2, and 1, 3, 2, and 1. And the next argument has the points where you want to evaluate this function. In this case, you want to evaluate at 5, 7, and 9. And when you return it, you see the answer for each of the values of x at x equals 5, x equals 7, and x equals 9. So as you can see, it can be used for one or more values that you want to evaluate the function at. This is the polyval function. All right, so those are very useful functions. We're going to use them going forward. Remember, we talked about the roots function to find the roots of a function. We talk about the poly function to find or to define a polynomial coefficients from your roots. We talk about the f0 function to find the zeros of a function where the function crosses 0. And we also talked about the polyval function to evaluate a polynomial or a function at a specific point. All right. Next thing I want to talk about is a couple of functions called one is called the inline function, and the other one is called the anonymous function. And before we start, I'm going to tell you, the anonymous function is the one that is really useful, more useful, and the one that we're really going to be focusing on going forward. The inline function, by the way, every now and then MATLAB retires functions, okay? Either because they change the function, made them a lot more efficient, and it's got more features, and so they retire a function because already something better is doing a job that can do more, right? So it's not unusual that you go from version to version and not find a particular function. So the reason I'm including the inline function is because you still may find it in earlier versions. In fact, they haven't retired yet, but they're planning on retiring the inline function. But the reason I'm including it is because, first of all, your book uses it, and some of the books still use it, but the anonymous function will replace it entirely. So for now, you can use both, but in the future, I think there are plans for MATLAB to retire the inline function. But at the end, you'll see that you can do the same thing with both functions, okay? So with that said, let me define the inline function. So the inline function lets you create a function of any number of variables by giving a string that has the function followed by a series of strings showing the order of the input variables. The ultimate goal of this is that you are going to create like a macro. If you take in programming in any way, you probably remember what a macro is. A macro is just a shortcut for a much larger function or a much larger set of commands that you use, right? So this is basically what inline and anonymous does. It creates a macro. It creates a shortcut to do a set of more complicated steps or commands into a more condensed way. So you use an inline function, like I said, as a kind of macro. Instead of typing a lot of information every time, you define the inline function once, and then use the function to perform all the extra typing. An anonymous function is even shorter. It's an even shorter version of the inline function. It can contain a single executable statement, and the single statement can take input arguments and provide output data. And that's where the at symbol comes in, as I mentioned to you previously when we used the F0 function. When we create anonymous functions, we use the at symbol. The at symbol identifies the code that follows as an anonymous function. It's a macro, okay? Any input arguments you want to accept must appear in parentheses that follow the at symbol. And we'll see some examples in just a minute. This is just for your reference later, if you want to reference that. But once you start using it, you see that it's kind of obvious how to use it. So you generally use anonymous functions for very short pieces of code that you need to use, very repetitive. Inline functions execute more slowly than anonymous functions. And I think that's why you'll see that inline functions will be replaced. So whenever possible, we're going to use anonymous functions instead, okay? But again, you can achieve the same result, but inline functions are a little less, they're slower. They're less optimized, if you will. So let's see. So to give the anonymous function a name, we put the function's name on the left side of an equal sign. So this will be the name of the function, right? And the anonymous function on the right. So, and this is the format, right? We have the name of the function on the left. That will be the ultimate name that we're going to use for that function. We have a list of arguments in parentheses preceded by the at symbol. And then we have the expression we want to replace by this name. We're basically replacing an expression by just a single name. And we tell them what arguments that expression has. Okay, I hope that makes sense. So, and we'll do an example. Now, one point to remember, and we'll see this in the example, is that anonymous functions are unaffected by any variable change after the function is defined. We'll see how that works, right? So in this case, right, we have, we really have a function ax squared plus by squared, right? And so, let's say we're going to use this function a lot of times, right? And, if you're not using a script or anything, you don't want to keep typing, ax squared plus bx plus by squared every time you want to perform that operation, right? And this is a simple example, but, it goes into using it for more complicated cases. So, so this is the function that we want to use, ax squared plus by squared. We define a as 2, b as 3, okay? And so these are the list of the arguments that are included in the function itself, right? We have variables rather. We have two variables, x and y, that are part of the function here, right? The expression, if you will. So And this is the format of the anonymous function. So when you see the @ sign, that implies an anonymous function. Is, again, we're using a macro, right? So now at the end of this statement here, we have replaced sample, or rather, we have replaced the entire function here by just one name sample. So every time you use sample, right, you really call in this function with these two variables. In this case, the A and B has already been defined as 2 and 3. So as you can see here, when you call sample, this is the argument list you're going to pass, right? In this case, you have 2 and 1, okay? And when we call it, as you can see here, this obviously, this will means for x equals 2 and for y equals 1, right? So when we call this sample function, it's going to evaluate what sample defines is going to evaluate ax squared plus by squared, where a has already been defined as 2, b has already been defined as 3, but it's going to evaluate that function at 2 and at 1. And of course, you get the result, right? It's 11. And obviously, you have 4 times 2 is 8, plus 3 times 1 is 3, so that gives you 11, right? So now, this is the core of what the anonymous function does, right? And that's what I wanted to make sure you understand, that is replacing sample by this entire function here, okay? And the other point I made previously that says, well, an anonymous function is unaffected by any variable changes after the function is defined. In other words, the function is defined in this line, right? After the function is defined, notice here that we change the values for A and for B. Instead of being 2 and 3, now it's 5 and 0. And I called the sample function again with the same values for x and y, but this time it returned the same result. The reason for that is because after the function has been defined, any changes that I made to the variable itself are not seen by the function. It's only seeing whatever precedes the definition of the function, see? Okay. So if I wanted to make a change here, I need to redefine the function again, okay? So I can see, another result. All right. Inline functions don't use the @ symbol, okay? They're very similar, but they not use the @ symbol. And is different. As you can see, it uses characters to define some of the functions, for instance. But at the end result, you get the same outcome. So inline functions are good for simple functions that will not be used that often, and can be written in a single expression. But again, notice that anonymous functions are more common, okay? But again, this is something you should know because you're going to find inline functions still being used in a lot of the literature. And the format of the inline function is that you have, of course, everything that you define in the inline function is going to be assigned to some sort of name. Remember, that name is replacing the activity that's going on the right-hand side, remember, right? Like the anonymous function replaced in the previous example, replace the entire function a squared plus by squared plus for one name only. It's the same idea here, right? And here you call, or you use the inline function without the @ and you define inside as the in parentheses, you can have an expression. That expression in single quotes, which defines the function or the entire expression you want to replace. And then you're going to have the function variables, which are the arguments for that expression, also in single quotes, as you can see here. So expression is the expression to be evaluated, and whatever follows are going to be the function variables. So you can see that the the sort of the format is the same as in the anonymous function, but it's just in a different way, right? So in this case, let's say we want to evaluate the function x to the cube minus y to the cube, right? So again, the expression here, and it's in single quotes, is going to be x to the third minus y to the third. And the variables, again, in single quotes are x and y. And so when I call the inline function, right? Like in this case, I have with the variables x, y, and this is going to be again my function, right? X to the third minus y to the third, and I'm going to pass the variable values of 3 and 2. Then the answer again evaluates just to 19. Okay, it's very similar to the anonymous function, but is a little different in the way you define it. I noticed there was an extra line when I was showing you the example for this expression, x to the third plus minus y to the third. So I fixed that, and this is the correct output that you should be seeing. There was an extra line in that previous slide, so you're not going to see that information in the when you see the slide information, but you're still going to see it in as part of the video. But this should be the correct information. So let me just go over that again. So the inline function again, by the way, the way we define the inline function is correct. It's just that the output was showing an extra line for some reason. So in any case, this definition is correct. We are using the inline function to define this expression, x to the third minus y to the third, in single quotes, with the variables in single quotes also, x and y, which are part of the expression. And we are replacing this entire information by just one variable, and we give that variable the name z. So as you can see, once we define z as this expression, anytime we call it, and we give it a value for x and y, it gives you the answer. It evaluates the function at those 2 points. And I'm showing you here 3 different cases where by simply calling z with those argument, different arguments in each of these cases, it evaluates the function x to the third minus y to the third at those values, which is what we intended. Okay, so I hope that you can see that inline functions and anonymous functions are just a way of shorting things out, making it easier to define much larger statements, much larger expressions into something that is simple to use, right? Like in this case, the sample is the name that we're given to this expression using the anonymous, and in this case, we gave the expression that we're going to evaluate just the variable named z. Okay, and anytime we use z from now on in your program is defined, by this inline function. Now, obviously, when you come back to if you close MATLAB, it's not going to save it, right? There's a way to save your own definitions, and we'll see that later. But if you haven't done that yet, then you're going to have to rerun the inline if you want to reuse this again as it is. Okay. All right. So I want to get started with the next topic, which is plotting. And we are already familiar with the simple plot, right? We used this previously, just the plot xy to plot a simple function. When we've been using this plot in the past, this plot function, remember, we haven't really been defining or telling the function, what to put the title, how to use the title, what labels to, how to place the titles in the plot, and so forth. We did that manually in one example, if you remember, which is also something you can do once the plot is once the plot is done, is generated. But there's a way, obviously, as I told you at that time, to do this programmatically, if you will. And so we use some commands within the plot function. For example, title, X label, and Y label determine or tell the plot function what information to place in the plot. So in this example, title in single quotes, in parentheses, example 1 will show us the title. X label, again, you define it in single quotes, in parentheses, will place time, comma, second, SEC. Y label in this case, again, in parentheses, single quote, will place distance, comma, ft along the y-axis. And of course, the grid on will keep the grid in the expression if you want to have a grid, right? So a couple of things to remember about plotting is that if I use the figure command, it'll open a new figure window. And every time it opens a new figure window, it's going to give it a new number by default. Okay, that's if you want to have separate, if you want to see plots in different figures, right? Generated independently, as opposed to seeing all the plots in one single plot. So one single figure. So that's an option that you can use. So executing figure without an input parameter will, again, causes a new window to open, and it's going to be numbered consecutively, one higher from the current window. Okay. We'll see examples of this in a minute. Hold freezes the current plot so that any additional plot can be overlaid, right? If you want to overlay different plots onto the same figure, you use the hold command. And then you have the options of hold on and hold off. The hold on command can be used to layer plots onto the same figure. And then MATLAB will continue to layer the plots until it sees a hold off command. If you have one, you don't have to have one if you don't want to stop. So you can run, for instance, a set of commands to have 3 plots on one figure. You go hold on, hold off at the end, and then start again to have maybe another plot with 3 different figures, 3 different plots in another figure. So you use the hold on, hold off to manipulate how you want to see the figures, the plots on that figure. All right. Also, one thing to remember is that as you type commands into MATLAB, you notice that the text color changes to red when you enter a single quote. This is important because you're going to be using single quotes a lot. This tells you that you are studying a string, okay? So it turns into red. The color is going to change to purple when you type the final single quote, and that's going to indicate you have completed the string. So if you pay attention to this visual aids, it's going to help you avoid coding mistakes. And again, MATLAB kind of guides you in that direction when you're writing code like that, commands like that. It gives you a lot of clues, right? So remember that, again, that when you start a single quote, the text color changes to red when you enter a single quote, and then it changes to purple when you type the final quote. Okay, little things like that will help you along the way. So another way to create a graph with multiple lines is to request both lines in a single plot command. MATLAB interprets the input to plot as alternating x and y vectors. For example, excuse me. In this case, we have plot, and in parentheses, we have x1 y1, comma, x1, comma, y1, comma, x2, comma, y2, comma. And in this case, this is telling MATLAB that the variables x and y1 form a ordered set of plots of values that can be plotted. And x2 and y2 is just another set of plots that will also can be plotted. For example, we're going to generate 3 cosine waves, 4 cosine waves rather, and we are going to go from a value of x from 0 to 2 pi in increments of pi over 100. Right? That's what we want to evaluate the cosine function at every one of those steps. So we define y1 as 2 times cosine x, y2 as 3 times cosine x, y2, I'm sorry, as 3 times cosine x, y3 as 4 times cosine x, and y4 as 5 times cosine x. So we have, obviously 1x to associate with each of the cosine functions. And we have 4 different y expressions, right? So the way to do that in one single command is to have plot, using plot, is to simply just, define xy1, xy2, xy3, or place those variables inside the parentheses. And MATLAB understands that, xy1 is one single set of values to be plotted. xy2 is another set of values, xy3 and xy4. And if we do that, you'll see the result on the right-hand side here with the 4 plots, the 4 different plots. Of course, all of them have over the same range of x, right? Okay. Now, the next command is mostly to show you the power of MATLAB and just just to show you how quickly can do things that may take a lot of time to do otherwise. And one of those functions that can show you that is called peaks. So peaks is a function of 2 variables and obtained by translating and scaling Gaussian distributions. More on that much later. That's not a critical point at this time. But it's mostly for demonstrating how MATLAB can create very powerful plotting with functions like this. So in this case, for example, if we use this peaks function, and n, by the way, is an n by n matrix. I'm sorry, it returns an n by n matrix, this peak function. In this case, if you give it a number 100, right, it creates a 100 by 100 matrix. And what it does is that 100 by 100 matrix it creates, every column in the matrix is plotted using this peaks function. And what we've done here is we simply said, well, plot, and you can place it in a variable if you want, right? In this case, it places in the variable z. So in this first example, when we use peaks, it creates internally, excuse me, it creates a 100 by 100 matrix, and each of those columns is plotted. See? So what you have here is 100 plots. Hard to see, but there's 100 plots here, one for each of the columns generated by this peaks function. We have increased that number to 150 here. So you have 150 by 150 matrix. And so what the peaks function is doing is creating that matrix 150 by 150, and each of the columns is then plotted. So in this case, you have 150 plots, 150 different plots, right? And you can see here that, it's, and this is done very, very quickly in MATLAB. So it's just to show you some of the powerful things you can do with MATLAB when it comes to plotting. It's very powerful. And we'll see more of this when we get into 3-dimensional plots and some of the surface plots that you can create with MATLAB. All right. So if the input to the plot command is a single array of complex numbers, for example, MATLAB is going to plot the real component on the x-axis and the imaginary components on the y-axis. So in this case, we have a matrix of complex numbers, of course, defined by this expression here. So since the array is just an array of complex number, when we plot it, okay, then it's going to plot, it's going to plot the real part on the x-axis and the imaginary part on the imaginary axis. This is the same as if we change, and we're going to talk a little later more into how we can go from a line to just show you the dots here. Okay, but for now, just understand that these two show the same result, these two plots. On the left-hand side, every point, which has 4 points actually on the plot, is joined by a line, right? So that you see a continuous line here when you do plot A. If we define the plot in a different way, we'll see later, where we can indicate where the actual points are located. You can see it from the array, right? We have 0, 0. We have 1, 2. So 1 again is the x-axis. 2 is it's in the imaginary axis. So it's 1, 2, y. And then we have 2, 5, y. And then we have 3, 4y. So this shows you, right, the real versus the imaginary parts in the plot. If the array itself is already imaginary, the plotting function, the plot function understands that, and it gives you these results. Okay. Some more plotting things, commands that we can do. For example, like in the previous slide, I used this O, right, to pinpoint where the points are located, right? There are other symbols that you can use, right? I use this one, the circle, right? As an indicator, you can use X, you can use a plus, you can use a star, you can use a square, diamond, triangle down, triangle up, so forth, right? Many other symbols or indicators to show or to indicate where the points may be located. You can also change the colors of your lines, right? As you can see here, by an indicator, with each color, blue is B, green is G, and so forth, right? So you can change that. And you can also change the line type. So if you want a solid line, use a dash. If you want a dashed line, you use a double dash, and so forth. So if you don't specify the line, then there won't be a line, like I did before here. So, this is again for your reference, and this is how you can make your plots look better and look different. Like if you want to, if you have different plots on the same figure, you may want to differentiate between the different points or the different plots that you have by color or by the indicator or the symbol you're using. Like in this case, right, we have different colors to indicate the plot. And then we haven't shown you that here, how we got that in here, but I'll show you later how you can control the colors. Like I said before, using that table that indicates what color can be associated with each of the lines. All right. And this is an example, right? In this first example, X varies from 1 to 10, and Y has these numbers associated with them, right? They come from somewhere. It's just a set of values associated with Y. And then if I say plot XY, and I follow it by in quotes, always in single quotes, and I have a double dash, right? And I have D and R. The double dash means the type of line I'm using. The D, right, if you noticed before, the D is the diamond, right? So it's going to have a type diamond. And the color I used, it was DR, so it's going to be red. So as you can see, is red, right? So I have double dash, right? The line type is going to use a type diamond as an indicator, and it's going to be red. So dash dash DR shows that expression, or the plot rather, in that way. We're going to do the same similar thing, right, with the x going over the same range. In this case, y again is the same values as before. And I'm going to generate another line, y2, which is the same as y1, but it's just shifted by 5 units up. In this case, I'm going to plot. I'm going to use the plot function to plot both plots on the same figure. Okay, and again, I'm going to have xy1 to define, the first set, and xy2 to define the second set. But for the first set, I'm going to keep the same settings that I had before, the dash dash dr. So I see this dash diamond red, right, to indicate y1. And then I'm going to use column star m. And again, if you go back to that table, right, this will indicate a dotted line. And I have M, which is magenta. And I have, what else did I have? M, and the star, right? Which we'll put a star on each of the points that are being plotted. So I have star, magenta, and dotted line. See? So that's how you can make your plots, look different and differentiate between different functions if you need to. Okay. All right. I'm going to stop at this point, and I'll continue with the same topic, plotting, on the next lecture.